More than 15 billion miles from Earth, a machine the size of a compact car is hurtling through interstellar darkness at 38,000 miles per hour. It was built to last 5 years. It is still travelling. It carries no fuel for return. It has no destination. No one is steering it. Within the next decade, its power will fail, its instruments will go silent, and it will continue drifting, alone, undetectable, and unreachable for longer than human civilization has existed. Not for centuries, not for millennia, for millions of years, and no one can stop it. This is the terrifying truth about humanity's longest journey. If you find cosmic explorations like this as haunting and beautiful as I do, it would mean a lot if you hit that like button and subscribe. Now, settle in, get yourself comfortable, let's begin. In the summer of 1977, 2 spacecraft left Earth on trajectories that would never bring them back. They were not the largest machines NASA had ever built. They were not the most expensive. They carried no human crew and required no life support. Each one weighed roughly 820 kilograms, about the mass of a grand piano, and stood a little taller than an average adult when measured from base to the top of the high-gain antenna. They were designed for a 5-year primary mission. They were not designed to return. That fact, so simple, so easy to overlook, is where this story truly begins. Because everything terrifying about the Voyager program grows from a single engineering reality. These machines were pointed outward, given velocity, and released. No braking system, no return trajectory, no plan for retrieval. From the moment they cleared Earth's gravitational influence, they were on a one-way course into the outer solar system and, eventually, beyond it. Every mile they travelled took them farther from the only world that knew they existed. Every second of thrust committed them more deeply to a departure that could never be undone. Most people remember Voyager for its photographs, the swirling storms of Jupiter, the razor-thin rings of Saturn, the pale blue crescent of Neptune hanging in blackness. These images changed how humanity understood its own solar system. But the photographs were a product of the first 5 years. The mission has now lasted more than 47 years and counting. The probes have travelled farther than any human-made object in history. They continue moving at this moment, right now, as you hear these words. And they will keep moving long after the last instrument shuts down, long after the last signal fades, long after the institution that launched them ceases to exist. This is what humanity's longest journey means. It refers to 3 things simultaneously, and each one deserves its own weight. First, Voyager 1 holds the record for the farthest distance ever travelled by a human-made object, currently more than 15 billion miles from the Sun, a number that increases by roughly 1 million miles every single day. Second, the Voyager program represents the longest continuous mission duration in the history of spaceflight, operating without interruption since launch. Third, and this is the part that changes the story, the mission continues beyond its original science objectives, beyond the functional lifespan of its instruments, into a phase that no one fully planned for. The probes are still going, not because someone decided they should, because no one can stop them. The story of how this happened starts not with engineering, but with celestial mechanics. In the late 1960s, a young aerospace engineer named Gary Flandreau was working at the Jet Propulsion Laboratory in Pasadena, California. His assignment was straightforward: calculate whether a spacecraft launched in the late 70s could use the gravity of one planet to reach the next. What Flandreau discovered was something far more extraordinary. He realized that Jupiter, Saturn, Uranus, and Neptune were approaching a geometric alignment that occurs approximately once every 176 years. A spacecraft launched during a narrow window in the late 1970s could use the gravitational pull of each planet to accelerate toward the next, visiting all 4 gas giants in a single mission. Without this alignment, Reaching Neptune alone would require a flight time of roughly 30 years. With it, the same journey could be accomplished in 12. This alignment created what engineers called the Grand Tour, a trajectory concept that would slingshot a probe from planet to planet across the outer solar system, using each world's gravity as a free accelerator. The mathematics were elegant but unforgiving. Each flyby had to occur within a precise window. Arriving at Jupiter a few days late could mean missing Saturn entirely. The gravitational assists formed a chain, and every link had to hold. The opportunity was once in a lifetime, literally. No human alive during the planning phase would live to see the next alignment. If this window closed without a launch, the chance would not return until the 22nd century. The physics that made the Grand Tour possible deserve a moment of explanation, because they reveal something fundamental about how Voyager achieved its velocity, and why that velocity is permanent. A gravitational slingshot, more formally called a gravity assist, works by exploiting the orbital motion of a planet. As a spacecraft approaches a planet, it falls into the planet's gravitational well, accelerating as it descends, exactly as a ball accelerates when dropped from a height. As it swings past the planet and climbs back out of the gravitational well, it decelerates by the same amount. If nothing else were happening, the encounter would be a wash. Speed gained on approach equals speed lost on departure. But the planet itself is moving. It is orbiting the Sun at tremendous velocity. The spacecraft's trajectory is bent by the encounter, and if the geometry is arranged correctly, the probe exits the encounter travelling faster relative to the Sun than it entered, having effectively stolen a tiny fraction of the planet's orbital momentum. The planet, in exchange, slows down by an amount so infinitesimal it could never be measured. Jupiter, for example, lost roughly 1 foot per trillion years of orbital velocity from Voyager's flyby. The spacecraft gained thousands of miles per hour. This asymmetry, trading an unmeasurable planetary slowdown for a dramatic spacecraft acceleration, is what made the outer solar system accessible within a human lifetime. NASA initially proposed a dedicated Grand Tour program involving 4 large, ambitious spacecraft. Budget constraints and congressional skepticism killed the full plan. What survived was a more modest proposal: 2 smaller, cheaper probes that would attempt a scaled-down version of the same trajectory. They were originally called Mariner Jupiter-Saturn, reflecting the limited ambition that budget realities imposed. Only later were they renamed Voyager, a name that would prove far more prophetic than anyone intended. What was lost when the full Grand Tour died in the budget process is worth noting, because it illuminates the trade-offs that shaped everything Voyager became. The original plan called for 4 spacecraft, 2 pairs, launched on complementary trajectories, providing redundancy and broader coverage. One pair would visit Jupiter and Saturn before continuing to Pluto. The other would target Jupiter, Uranus, and Neptune. The spacecraft themselves would have been larger, more capable, and equipped with more advanced instruments than what Voyager ultimately carried. Congressional budget pressures in the early 1970s, driven partly by the cost of the Vietnam War and partly by declining public enthusiasm for space spending after the Apollo program, killed the ambitious version. What survived was a compromise: 2 smaller, cheaper probes officially tasked with visiting only Jupiter and Saturn, though engineers quietly designed Voyager 2's trajectory to preserve the option of continuing to Uranus and Neptune if the spacecraft survived and funding held. The Pluto flyby was abandoned entirely, a decision that would not be rectified until the New Horizons mission arrived at the dwarf planet in 2015, nearly 4 decades later. Every capability that Voyager carried, and every capability it lacked, traced back to choices made in budget meetings in Washington during the early 70s, decisions that locked in the parameters of a journey lasting longer than any of the decision makers would live. The engineering behind both spacecraft was extraordinary for its era, and remains remarkable even now. Each probe carried 11 scientific instruments, including cameras, ultraviolet and infrared spectrometers, magnetometers, plasma detectors, photopolarimeters, and cosmic ray sensors. The onboard computers operated on roughly the same processing power as a modern key fob, approximately 69 kilobytes of total memory. The software was stored partly in hardwired command sequences and partly on onboard systems that could be reprogrammed from Earth via radio uplink. This reprogrammability would prove essential decades later when engineers needed to adapt the spacecraft for missions they were never designed to perform. Communication relied on a 23-watt radio transmitter, producing a signal with roughly the power of a refrigerator light bulb. That signal, traveling at the speed of light, takes more than 22 hours to reach Earth from Voyager 1's current position. By the time it arrives, it has weakened to less than a billionth of a watt. Detecting it requires the Deep Space Network's largest antennas, 70-meter dishes positioned in California, Spain, and Australia, operating with cryogenically cooled receivers, sensitive enough to distinguish the signal from the background hiss of the cosmos. Power came not from solar panels, useless at the distances Voyager would reach, where sunlight dims to a fraction of a percent of its intensity at Earth, but from 3 radioisotope thermoelectric generators, each containing several pounds of plutonium-238. The natural radioactive decay of this isotope produces heat, which thermoelectric couples convert into electricity through the Seebeck effect. At launch, the 3 generators combined provided approximately 470 watts of electrical power, enough to run a handful of household light bulbs. That output decreases by roughly 4 watts per year as the plutonium decays and the thermoelectric materials degrade. This steady, irreversible decline in power is the ticking clock at the heart of the entire Voyager story. Every watt lost is a capability that can never be recovered. The people who built these machines understood what they were creating. The Voyager engineering team at the Jet Propulsion Laboratory numbered in the hundreds during the peak design and assembly years, and many of them were remarkably young. Engineers and technicians in their 20s and 30s, assembling hardware they knew they would never touch again once it left the clean room. John Cassani, the original project manager, later recalled that the team carried an awareness throughout the build process that every component they soldered, every cable they routed, every thermal blanket they attached would eventually travel farther from human reach than any object in history. There would be no service calls, no upgrades, no recalls. If a solder joint failed at Saturn, there was no fixing it. If a capacitor degraded at the heliopause, there was no replacement. The spacecraft had to work, had to keep working, in conditions that no engineer could fully simulate and at distances that no repair crew could ever bridge. This imposed a discipline that bordered on obsession. Redundant systems were built into every critical pathway. Backup receivers, backup command decoders, backup thrusters. The attitude control system could operate in multiple modes depending on which components survived. The onboard computers, and there were 2 per spacecraft, primary and backup, could be reprogrammed from Earth if a failure demanded workaround software that had not existed at launch. The engineering philosophy was not optimism, but pessimism applied constructively. Assume everything will eventually fail, and design the spacecraft to keep functioning anyway. That philosophy, adopted by young engineers who could not have imagined the world of 2025, is the reason the probes still operate nearly half a century later. The machines outlasted not only their 5-year design life, but the careers, and in many cases the lifetimes, of the people who built them. But in those early years, power was abundant and the science was staggering. Voyager 1 reached Jupiter in March of 1979, about 18 months after launch. What it found shattered assumptions that had stood for centuries. The Great Red Spot, long known through telescopic observation as a persistent atmospheric feature, revealed itself in close-up photography as a colossal anticyclonic storm, large enough to contain 2 or 3 Earths side by side, with wind speeds exceeding 400 miles per hour at its edges. The storm's internal structure showed layers of turbulence and colour variation that no ground-based telescope had ever resolved. Jupiter's atmosphere turned out to be far more dynamic and violent than models had predicted, a churning ocean of hydrogen and helium driven by internal heat that the planet radiates in excess of what it receives from the Sun. But the true shock came from Jupiter's moons. Io, the innermost of the 4 large Galilean satellites, was caught in the act of volcanic eruption. Navigation engineer Linda Morabito, examining an image of Io's limb to check the spacecraft's position, noticed a strange plume rising above the moon's edge. Cameras captured towering eruptions of sulfur and sulfur dioxide rising more than 300 kilometers above the surface, volcanic explosions on a scale that dwarfed anything on Earth. Before Voyager, no one had confirmed active volcanism on any body in the solar system other than our own planet. Io changed that permanently. The moon's surface was young, constantly resurfaced by lava flows, with no visible impact craters, a world being remade in real time by tidal heating from Jupiter's immense gravity. Europa revealed something equally startling. Its surface was a cracked, refrozen shell of water ice, remarkably smooth and almost entirely free of craters. The pattern of fractures resembled ice flows on a frozen sea, suggesting that beneath the surface lay a liquid water ocean, an environment maintained by tidal heating similar to that driving Io's volcanism, but expressed as warmth rather than eruptions. Decades later, Europa would become one of the primary targets in the search for extraterrestrial life, but the initial suggestion came from Voyager's photographs. Ganymede turned out to be the largest moon in the entire solar system, bigger than the planet Mercury, with a complex surface showing both ancient dark terrain and younger grooved regions suggesting geological activity in its past. Callisto displayed a surface so ancient and so densely cratered that it appeared to have remained essentially unchanged for billions of years, a frozen museum of the solar system's early bombardment history. Voyager 2 arrived at Jupiter 4 months later and confirmed every major finding while contributing new data on the planet's faint ring system and the complex structure of its magnetosphere, the largest single structure in the solar system, a magnetic bubble so enormous that if it were visible to the naked eye, it would appear larger than the full moon from Earth's surface. Both probes then used Jupiter's gravity to accelerate towards Saturn, picking up speed without burning a single drop of fuel. At Saturn, the discoveries intensified. The ring system, long admired through telescopes as a seemingly simple set of broad bands, revealed itself as a structure of staggering complexity. Thousands of individual ringlets, gaps, density waves, braids, and transient features called spokes that appeared and disappeared on timescales of hours. Shepherd moons were discovered orbiting within and alongside the rings, their gravitational influence sculpting ring material into narrow, sharply defined bands. The F-ring, a thin strand outside the main ring system, displayed bizarre kinks and clumps maintained by 2 small moons orbiting on either side, a gravitational ballet that no one had predicted. Titan, Saturn's largest moon, proved to have a thick nitrogen-rich atmosphere with a surface pressure roughly 1.5 times that of Earth, the only moon in the solar system known to possess a substantial atmospheric envelope. The atmosphere was so opaque with organic haze that cameras could not penetrate to the surface, a mystery that tantalized scientists and would not be resolved until the Cassini-Huygens mission arrived nearly 3 decades later. But Voyager's instruments detected complex organic chemistry occurring in Titan's upper atmosphere, methane and nitrogen combining under ultraviolet radiation to produce a smog of hydrocarbons that rained down onto the surface. The discovery suggested a world with a complex chemical cycle that bore eerie resemblances to the prebiotic chemistry that may have preceded life on early Earth. After Saturn, the missions diverged in a way that would define their separate destinies. Voyager 1's trajectory at Saturn was designed to achieve a close flyby of Titan, which required a path that deflected the spacecraft sharply upward, out of the plane of the solar system. This angle provided the best Titan observations, but ended Voyager 1's ability to visit any more planets. Its grand tour was over. It was now heading north, away from the ecliptic plane, toward interstellar space. Voyager 2, having taken a different path past Saturn that sacrificed the close Titan encounter, retained the geometry needed to continue outward. it became the only spacecraft ever to visit Uranus and Neptune. The Uranus encounter in January of 1986 remains one of the most underappreciated achievements in the history of space exploration. No spacecraft had ever visited the seventh planet. Everything known about Uranus came from ground-based telescopes that could resolve it as little more than a featureless blue-green disk. Voyager 2 discovered 10 previously unknown moons, studied the planet's unusual ring system, and mapped a magnetic field tilted nearly 60 degrees from Uranus's rotational axis and offset from the planet's center, a configuration so bizarre that it defied existing models of planetary magnetic field generation. Miranda, the smallest of the 5 major Uranian moons, displayed a surface so geologically tortured, with enormous canyons, fractured terrain, and features nicknamed coronae, that scientists initially speculated the moon had been shattered by a catastrophic impact and gravitationally reassembled. Uranus itself presented the mystery of its extreme axial tilt, nearly 98 degrees, meaning the planet essentially rolls around the Sun on its side, creating seasons unlike those of any other world. 3.5 years later, in August of 1989, Voyager 2 completed the grand tour with a flyby of Neptune, the most distant planetary encounter ever achieved. The results were breathtaking. Neptune, expected to be a cold, sluggish world receiving barely 1/900th the sunlight Earth enjoys, displayed the fastest winds ever recorded in the solar system, approximately 1,200 miles per hour. The Great Dark Spot, an enormous storm system roughly the size of Earth, was tracked across the planet's atmosphere, revealing dynamic weather patterns driven by an internal heat source that caused Neptune to radiate more than twice the energy it receives from the Sun. Triton, Neptune's largest moon, captured on a single close flyby that remains the only visit any spacecraft has ever made, revealed active geysers of nitrogen gas erupting from its frozen surface. Evidence of ongoing geological activity on a world where surface temperatures hovered around -235 degrees Celsius, making it one of the coldest measured surfaces in the solar system. With Neptune's flyby complete, the grand tour was finished. The planetary encounters that had justified the entire program, the photographs, the revelations, the paradigm-shifting data, were done. In 12 years, 2 small machines had rewritten the textbook on every giant planet in the outer solar system. They had discovered active volcanoes on a world thought to be frozen dead. They had found evidence of subsurface oceans where no one expected liquid water. They had revealed ring systems of extraordinary complexity, magnetic fields of baffling geometry, atmospheric dynamics that defied simple models, and moons with chemistries that hinted at the raw ingredients of life. The scientific return was incalculable. Hundreds of research papers, thousands of images, entire careers built on analysing the data these 2 probes returned. And then something happened that transforms this story from a triumph of exploration into something altogether more haunting. The probes kept going, not because a new destination awaited them, not because someone pressed a button to extend the flight. They kept going because there was no way to stop them. No braking system had ever been installed. There was no engineering reason to include one, and the mass penalty would have been prohibitive. No return trajectory had ever been calculated. The gravitational assists that made the grand tour possible were one-way accelerations. The probes were travelling at velocities exceeding 35,000 miles per hour relative to the Sun, fast enough to escape the solar system's gravitational grip entirely. They were on hyperbolic escape trajectories, meaning they had achieved more than enough velocity to overcome the Sun's pull. They would never loop back. They would never slow down enough to enter orbit around any object. They would fly outward, continuously, essentially, forever. NASA, recognizing that the still functioning instruments could study the space environment beyond the planets, formally renamed the continuing effort the Voyager interstellar mission in 1989. The scientific objective shifted from planetary science to heliospheric physics, studying the solar wind, cosmic rays, and magnetic fields in the outer reaches of the Sun's influence, with the ultimate goal of detecting the boundary where the sun's domain gives way to interstellar space. But underneath the official mission language, underneath the revised science objectives and the adjusted instrument configurations, lay a simpler and more permanent truth. The probes were leaving. They had always been leaving. From the moment they were launched on escape trajectories with no possibility of return, their departure from the solar system was a mathematical certainty. The only variables were how long the instruments would last, how long the power would hold, and how long anyone on Earth would be listening when the whisper finally became too faint to hear. This is the fact that anchors everything that follows. Voyager was never built to come home. It was built to fly outward, gather data during a brief window of planetary encounters, and then continue into the unknown on a trajectory that no force in the solar system could reverse. The engineering genius that made the Grand Tour possible is the same engineering reality that made the journey permanent. Every slingshot maneuver that accelerated the probes toward the next planet also accelerated them toward an exit from which there is no return. Every discovery they made carried them farther from the species that built them. Every photograph they took was composed during an act of irreversible departure. And here is what most people miss when they celebrate Voyager's achievements. The planetary encounters, Jupiter, Saturn, Uranus, Neptune, were the prologue. The real story is what happens after. The real shock is not how far Voyager travelled during its years of active science. It is how long the probes keep going after the science ends, after the power fades, after the signal dies, after the last engineer turns off the last receiver. The journey does not stop when the mission does. It continues on a timescale that makes every human institution look temporary, every civilization look fragile, and every lifetime look like the flash of a single spark in an infinite darkness. The probes are still out there tonight, still moving, still falling away from the sun at speeds that add roughly 1 million miles to their distance every day. The crossing of a boundary that no human object had ever reached would confirm that Voyager's journey had entered a phase that no one could plan for, no one could control, and no one could ever reverse. For most of human history, the edge of the solar system was a theoretical concept without a physical location. Ancient astronomers placed the boundary at Saturn, the farthest planet visible to the naked eye. Copernicus pushed it outward by reordering the cosmos around the sun. William Herschel extended it further in 1781, when he discovered Uranus, a planet so distant that it takes 84 years to complete a single orbit. Johann Galle added Neptune in 1846, following mathematical predictions that a massive unseen world was gravitationally tugging on Uranus's path. Clyde Tombaugh added Pluto in 1930, pushing the known boundary to a frozen speck orbiting nearly 40 times farther from the Sun than Earth. Each discovery stretched the map, but none of them answered the deeper question: where does the Sun's influence actually end, and what lies beyond? The answer turns out to be far more complicated and far more unsettling than simply drawing a circle around the outermost planet. The Sun does not merely sit in space radiating light and warmth, it exhales. Every second, the Sun releases approximately 1 million tons of charged particles, protons, electrons, alpha particles, and heavier ions in a continuous supersonic outflow called the solar wind. This wind races outward in all directions at speeds ranging between 300 and 800 kilometers per second, depending on solar activity and the region of the Sun from which it originates. As this torrent of charged particles streams outward, it carries with it the Sun's magnetic field, stretching it into an enormous spiral pattern that extends billions of miles into space. This outflow fills an immense bubble of solar-dominated material called the heliosphere. Everything inside the heliosphere, every planet, every asteroid, every comet, every grain of interplanetary dust swept along by the solar wind, belongs to the Sun's domain. The heliosphere is not just a region of space near the Sun, it is the Sun's physical presence in the galaxy. It is, in a very real sense, the Sun's atmosphere, a vast exhalation that defines our star's territory within the Milky Way, the way a country's borders define its sovereign land. To exist inside the heliosphere is to exist under the sun's direct physical influence. To leave it is to enter a realm where our star is no longer the dominant force shaping the local environment. Beyond the heliosphere lies something fundamentally different. Interstellar space is permeated by its own medium, a thin plasma of hydrogen and helium atoms, cosmic rays accelerated to tremendous energies by distant supernovae and other violent astrophysical events, and magnetic fields generated by galactic-scale processes that have nothing to do with our star. This interstellar medium has its own pressure, its own density, its own magnetic structure. It pushes inward against the heliosphere just as the solar wind pushes outward against it. The boundary where these two pressures balance, where the outward force of the solar wind equals the inward pressure of the interstellar medium, is called the heliopause. It is not a wall. It is not a membrane. It is a turbulent, shifting, dynamic transition zone that flexes and ripples with the sun's 11-year activity cycle, expanding when solar output increases and contracting when the sun grows quieter. For decades, scientists knew this boundary had to exist. They could model it. They could estimate its distance, roughly 90 to 120 astronomical units from the sun, where 1 astronomical unit equals the distance from Earth to the sun, approximately 93 million miles. They could predict what instruments should detect when a spacecraft approached it: a decrease in solar wind particles, an increase in galactic cosmic rays, a change in the magnetic field direction as the sun's field gave way to the interstellar magnetic field. But no instrument had ever reached that boundary. No measurement had ever been taken at the actual frontier. The heliosphere was understood in theory, mapped in simulation, and entirely unexplored in practice. Every textbook diagram of the heliosphere was, in the most literal sense, a guess. An educated, mathematically informed, physically grounded guess, but a guess nonetheless. The models disagreed on the precise distance. They disagreed on the shape. They disagreed on whether the transition would be sharp or gradual, smooth or turbulent. Answering these questions required something that no simulation could replace: a machine at the boundary, taking measurements in real time, reporting back what it actually found. But even having a machine at the boundary would be worthless without the ability to hear what it reported. And hearing Voyager at interstellar distances is an achievement almost as remarkable as getting it there. The Deep Space Network, 3 ground stations positioned roughly 120 degrees apart around the Earth in Goldstone, California, Madrid, Spain, and Canberra, Australia, was designed to maintain continuous contact with spacecraft throughout the solar system. Its largest antennas, 70 meters in diameter, are among the most sensitive radio receivers ever built. They operate with cryogenically cooled amplifiers that reduce electronic noise to levels approaching the quantum limit, and they employ a technique called signal integration, accumulating data over extended periods to pull coherent information out of a signal buried beneath the random thermal noise of the receiver and the cosmos. By the time Voyager 1's 23-watt transmission reaches Earth from its current distance, the signal has spread across a spherical wavefront, billions of miles in diameter. The power intercepted by even the largest antenna dish amounts to less than 1/10 of a billionth of a trillionth of a watt, a quantity so small that the thermal vibrations of atoms in the receiving equipment generate more energy than the signal itself. Distinguishing spacecraft data from this noise requires exquisitely precise frequency tracking. Error correction codes embedded in the data stream by engineers who anticipated this challenge decades in advance, and processing algorithms that can reconstruct a coherent message from fragments scattered across hours of recording. The fact that this works, that a 23-watt bulb can whisper across 15 billion miles and be understood, represents one of the quietest and most extraordinary engineering achievements in human history. Voyager 1 became that machine. By the mid-2000s, Voyager 1 had travelled farther from the Sun than any object in human history. It was beyond the orbit of every known planet, beyond the Kuiper Belt where Pluto and its icy neighbours circle, pushing into a region where sunlight was so dim that the sun appeared as nothing more than a particularly bright star. The spacecraft's instruments, though aging and operating on diminishing power, still functioned. Specifically, the plasma wave instrument, the magnetometer, the cosmic ray subsystem, and the low-energy charged particle detector. These 4 tools, designed in the early 1970s, built with technology that predated the personal computer, would become the key witnesses to an event that scientists had anticipated for years but could not predict with precision: the crossing of the heliopause. The approach was not sudden. It unfolded over nearly a decade of subtle, accumulating changes. Beginning around 2004, at a distance of approximately 94 astronomical units from the Sun, Voyager 1 crossed a preliminary boundary called the termination shock. This is the point where the solar wind, which travels at supersonic speeds through the inner heliosphere, abruptly slows to subsonic velocities as it begins to feel the back pressure of the interstellar medium. The crossing was confirmed by a sudden change in the behavior of the low-energy charged particle instrument. Particles that had been flowing smoothly outward became turbulent and chaotic, indicating that the solar wind had decelerated dramatically. Beyond the termination shock lay the heliosheath, the outermost layer of the heliosphere, a thick region of compressed, heated, turbulent solar wind plasma piling up against the interstellar medium like water, backing up behind a dam. Voyager 1 spent years traversing this region, and the data it returned was confusing. The magnetic field fluctuated, particle counts rose and fell unpredictably. Some instruments suggested the boundary was near, others indicated it was still far away. The heliosheath turned out to be a messier, more complex environment than anyone had modelled, a roiling frontier zone where solar and interstellar influences mixed in ways that defied clean categorization. The difficulty was compounded by a critical instrument failure: Voyager 1's plasma science experiment, the instrument specifically designed to measure the density, temperature, and velocity of the surrounding plasma, had stopped functioning in 1980. This meant the spacecraft was approaching the most important boundary in solar system physics, without the one tool best suited to detect the crossing. Scientists would have to infer the heliopause transition from indirect measurements, cosmic ray counts, magnetic field readings, and plasma wave data. It was like trying to determine when you had crossed from one country into another while blindfolded, relying only on the sound of the wind and the feel of the soil under your feet. The breakthrough came from an unexpected and beautifully indirect chain of events. In March of 2012, a massive coronal mass ejection, an enormous eruption of solar plasma, blasted away from the Sun's surface. This wave of charged particles raced outward through the heliosphere at roughly 400 kilometers per second. 13 months later, in April of 2013, the shock wave reached Voyager 1's location. When it arrived, it did something extraordinarily useful. It caused the surrounding plasma to oscillate, vibrating at a frequency determined by the plasma's density. Voyager 1's plasma wave instrument detected these oscillations and measured their frequency. The mathematics were straightforward. Plasma oscillation frequency relates directly to electron density. The result was unambiguous. The electron density surrounding Voyager 1 was approximately 40 times higher than what would be expected anywhere inside the heliosphere. The spacecraft was immersed in interstellar plasma. It had crossed the boundary. Working backward from this measurement and combining it with data from the magnetometer and cosmic ray instruments, scientists determined that Voyager 1 had actually crossed the heliopause on or around August 25, 2012, more than a year before the confirming data arrived. At that moment, the spacecraft was approximately 122 astronomical units from the Sun, roughly 11.3 billion miles. The signal confirming the crossing, travelling at the speed of light, took approximately 17 hours to reach Earth. The crossing itself had taken 35 years of continuous flight to achieve. The announcement, when it came in September of 2013, was global news. For the first time in human history, a human-made object had entered interstellar space. Headlines celebrated the milestone with language that suggested arrival, as though Voyager had reached a destination, completed a quest, planted a flag. But the scientific reality was both more nuanced and more consequential. Voyager 1 had not arrived anywhere. It had departed. It had crossed out of the only cosmic environment that anything human had ever inhabited and entered a domain that owes nothing to the Sun, nothing to the solar system, nothing to any process originating from our corner of the galaxy. Voyager 2 provided its own independent confirmation 6 years later. On November 5, 2018, at a distance of approximately 119 astronomical units from the Sun, Voyager 2 crossed the heliopause heading in a different direction, southward relative to the ecliptic plane, while Voyager 1 had travelled northward. Unlike its sibling, Voyager 2 still possessed a functioning plasma science instrument, which provided the first direct in situ measurement of the interstellar plasma density at the boundary. The data confirmed and enriched what Voyager 1 had suggested. The transition was surprisingly abrupt. Within approximately a single day of spacecraft travel, the solar wind particle count dropped by more than a factor of 1,000, while galactic cosmic ray intensity surged to its highest recorded levels. The ambient plasma density jumped sharply. The magnetic field shifted in direction, but, intriguingly, not in magnitude, suggesting that the solar and interstellar magnetic fields happened to be of similar strength at the crossing point, a coincidence that scientists had not predicted and are still working to explain. The plasma science instrument aboard Voyager 2 provided data that could not have been obtained any other way. Unlike Voyager 1, which had to infer the properties of the surrounding medium from indirect measurements, Voyager 2 directly sampled the plasma flowing past its sensors and returned a detailed portrait of the heliopause as a physical boundary. The instrument measured a sharp increase in plasma density, from roughly 0.002 electrons per cubic centimetre inside the heliosphere to approximately 0.05 electrons per cubic centimetre in the interstellar medium, occurring over a distance the spacecraft traversed in less than a single day. The transition was far more abrupt than many models had predicted. Some theoretical work had suggested the heliopause would be a broad, diffuse gradient spanning millions of miles. Instead, Voyager 2 found something closer to a wall, thin, sharply defined, and surprisingly stable over the time the spacecraft took to cross it. The plasma temperature on the interstellar side registered lower than expected, suggesting that energy dissipation processes at the boundary were not behaving as standard models assumed. These measurements generated a cascade of revised theoretical work that continues today, as heliophysicists attempt to reconcile decades of simulation with the first direct observations from the frontier itself. Together, the two crossings, separated by 6 years, occurring at different distances, in different directions, under different solar conditions, revealed something unexpected about the heliosphere's structure. The fact that Voyager 1 crossed at a greater distance than Voyager 2 suggested that the heliosphere is not a symmetric sphere but an asymmetric structure, compressed on the side facing the direction of the solar system's motion through the galaxy and elongated on the trailing side. The Sun moves through the local interstellar medium at approximately 26 kilometers per second, and this motion creates a ram pressure that flattens the heliosphere's leading edge, while allowing the trailing edge to stretch into a long tail, like the wake behind a boat moving through water, or the shape a soap bubble assumes when you blow gently on one side. But here is where the story requires a correction that most popular accounts fail to make. Crossing the heliopause is not the same as leaving the solar system. The phrase, "leaving the solar system," has been attached to Voyager's achievements so frequently and so casually that it has become almost synonymous with the heliopause crossing. This is technically misleading in a way that matters deeply for understanding the true scale of Voyager's journey. The heliopause marks the boundary of the Sun's particle influence, the edge of the solar wind bubble. But the Sun's gravitational influence extends enormously farther. Gravity does not stop at the heliopause. It does not stop at any particular distance. It diminishes with the square of distance but never reaches zero. The most distant gravitationally bound structures of the solar system are believed to be the objects of the Oort cloud, a hypothetical but widely accepted shell of icy bodies that surrounds the Sun at distances ranging from approximately 2,000 astronomical units at the inner edge to as far as 100,000 astronomical units at the outer edge. 100,000 astronomical units is approximately 1.6 light-years, nearly half the distance to the nearest known star. The Oort cloud has never been directly observed. Its existence is inferred from the orbits of long-period comets that plunge into the inner solar system on trajectories originating from these extreme distances. But if it exists as models predict, it represents the Sun's true gravitational frontier, the outermost reservoir of objects that orbit our star. Voyager 1, at its current distance of approximately 165 astronomical units, has not even reached the inner boundary of the Oort cloud. It has crossed the heliosphere but remains deep within the Sun's gravitational sphere of influence. To reach the Oort cloud's inner edge, it would need to travel roughly 12 times farther than it has already come, to pass through the Oort cloud entirely and reach truly unbound interstellar space, space where no solar system object orbits, where the Sun's gravity is no longer the dominant force, would require reaching approximately 100,000 astronomical units. At Voyager 1's current speed of roughly 17 kilometers per second, crossing that distance would take approximately 30,000 years. 30,000 years. To put that number in context, 30,000 years ago, the last ice age was approaching its maximum extent. Glaciers covered most of northern Europe and North America. Homo sapiens shared the planet with Neanderthals, who would not disappear for another 10,000 years. The oldest known cave paintings were just being created. Written language would not be invented for another 25,000 years. The entirety of what we call civilization, every city, every nation, every scientific discovery, every war, every work of art, occupies less than 1/6 of that time span. Voyager will spend 30,000 years just crossing through the Sun's gravitational backyard. This distinction between the heliopause and the gravitational boundary matters because it reframes the achievement in terms that are both more honest and more unsettling. Voyager has crossed into interstellar space in terms of the plasma environment. It has entered a region dominated by galactic particles rather than solar particles. The magnetic fields it detects are no longer generated by the Sun. The cosmic rays it measures originate from distant stellar explosions rather than from solar flares. In every meaningful sense related to the particle physics of its surroundings, Voyager has left the Sun's domain and entered the galaxy at large. But gravitationally, it remains bound to the Sun's broader influence for millennia to come. It is in a kind of cosmic limbo, beyond the Sun's breath, but not beyond the Sun's reach. It has left the house, but has not yet left the property, and the property, as it turns out, is unimaginably vast. So, what has Voyager actually entered? What is interstellar space like, now that we have direct measurements from two separate spacecraft? It is not what most people picture. The popular imagination tends toward two extremes, either a dramatic void of perfect emptiness, featureless black nothingness stretching between stars, or a luminous nebular landscape of colourful gas clouds and stellar winds. The reality is neither. Interstellar space, in the local region through which the Voyager probes are now travelling, is a medium. It is extraordinarily thin by any terrestrial standard, roughly 1 atom per 10 cubic centimetres, compared to the roughly 25 billion molecules per cubic centimetre in Earth's atmosphere at sea level. But it is not nothing. It is a physical environment with measurable, quantifiable properties. The local interstellar medium consists primarily of partially ionized hydrogen and helium gas, threaded through with magnetic fields of approximately 2 to 5 microgauss, roughly 100,000 times weaker than Earth's magnetic field, but real, present and measurable. It is laced with cosmic rays, high-energy protons, electrons, and heavier atomic nuclei that have been accelerated to near-light speeds by supernova shock waves and other energetic astrophysical processes occurring throughout the galaxy. These cosmic rays have been bouncing through the galaxy for millions of years, deflected by magnetic fields, gaining and losing energy through countless interactions. Inside the heliosphere, the Sun's magnetic field acts as a partial shield, deflecting many of these galactic cosmic rays before they reach the inner solar system. Beyond the heliopause, that shield is gone. Voyager now measures the full, unshielded intensity of galactic cosmic radiation for the first time. The temperature of the local interstellar medium is estimated at approximately 6,000 to 10,000 Kelvin. Surprisingly warm in absolute terms, but this number is deceptive. Temperature in such a diffuse medium refers to the average kinetic energy of individual particles, not to the sensation of heat. With only one atom per 10 cubic centimeters, the actual thermal energy per unit volume is negligible. A human body placed in this environment would not feel warmth. It would radiate heat into the vacuum and freeze, just as it would in any other region of deep space. The temperature is a statistical property of fast-moving but incredibly sparse particles. What makes this environment significant is not its physical properties in isolation, but what it represents in terms of Voyager's relationship to home. Inside the heliosphere, every particle, every magnetic field line, every gust of plasma traces back to the Sun. The environment is shaped by solar processes, flares, coronal mass ejections, the 11-year activity cycle, the rotation of the Sun's magnetic field. The heliosphere is the Sun's fingerprint on local space. Crossing the heliopause means leaving that fingerprint behind. It means entering a region where the dominant physical processes are galactic in origin. The magnetic fields are shaped by the Milky Way's large-scale structure and by the remnants of ancient stellar explosions. The particles have histories stretching back millions of years and billions of miles, originating from events that occurred long before the Sun existed and in regions of the galaxy that no solar system object will ever visit. The interstellar medium has existed for billions of years, far longer than our solar system, which formed only about 4.6 billion years ago from the gravitational collapse of an interstellar gas cloud. In a sense, interstellar space is the medium from which the Sun and planets were born. Crossing into it is not entering alien territory so much as returning to the primordial environment from which our entire stellar neighborhood once condensed. The Voyager probes are drifting through the raw material of future star systems, the same thin gas and dust that will, over millions and billions of years, clump together under gravity to form new stars, new planets, new possibilities for worlds, and perhaps for life. The specific region of interstellar space through which the Voyager probes are now travelling has a name and a history of its own. It is called the local interstellar cloud, sometimes referred to as the local fluff, a patch of partially ionized hydrogen and helium gas roughly 30 light-years across, with a temperature of approximately 6,000 Kelvin and a density somewhat higher than the average interstellar medium. The cloud is believed to have been shaped, and possibly created, by ancient supernova explosions in the nearby Scorpius-Centaurus stellar association, a loose grouping of young, massive stars located a few hundred light-years from the Sun. Those explosions, occurring over the past 10 to 20 million years, swept up surrounding gas and compressed it into structures that include the local interstellar cloud and several neighbouring clouds. The Sun entered this cloud relatively recently in cosmic terms, perhaps within the last few tens of thousands of years, and is expected to exit it within roughly 10,000 to 20,000 years, entering a somewhat different interstellar environment with different density and temperature characteristics. Voyager, travelling faster than the Sun relative to the local medium, will exit the cloud sooner. But neither the probes nor the Sun will notice the transition in any dramatic way. The change will be measured in fractions of an atom per cubic centimetre, a shift so subtle that only the most sensitive instruments could detect it, and by then, Voyager's instruments will be long dead. The interstellar medium does not respond to Voyager. It simply exists, vast and ancient and utterly unconcerned with the tiny objects passing through it, and this medium will persist long after our sun has died. In approximately 5 billion years, the sun will exhaust its hydrogen fuel and expand into a red giant before shedding its outer layers and contracting into a white dwarf. The heliosphere will vanish. The solar wind will cease. The bubble that currently protects the solar system from the full intensity of the interstellar medium will pop, and the space currently occupied by the planets will be flooded with galactic cosmic rays and interstellar plasma. But the interstellar medium itself will endure, modified, recycled, enriched by the sun's death and the deaths of countless other stars, but fundamentally persistent. The environment Voyager has entered will outlast the environment it left. There is something quietly staggering about this. Two machines built by a species that has existed for roughly 300,000 years have crossed into an environment that predates their star and will outlast it. The heliosphere, the only cosmic home humanity has ever known, is temporary. The interstellar medium is, on any human timescale, permanent. Voyager has crossed from the ephemeral into the enduring. But the enduring in this case is also the indifferent. Interstellar space does not know the Voyager probes are there. It exerts no special force on them. It has no landmarks, no features, no destinations that matter to a small machine with no functioning instruments. And here is the thought that should anchor the scale of what has happened. The heliopause crossing was a genuine scientific milestone. It confirmed decades of theoretical work. It provided the first direct measurements of the interstellar plasma and magnetic field. It demonstrated that a spacecraft built with 1970s technology could survive for decades in an environment it was never designed to explore, and return data of extraordinary scientific value from a region no human instrument had ever sampled. The achievement deserves every word of praise it has received, but the heliopause, that hard-won, celebrated boundary, represents a nearly negligible fraction of the distance the probes will eventually travel. If you represented the distance from the Sun to Voyager 1's current position as the width of a single human hair, the distance to the nearest known star would stretch roughly the length of a football field. The probes have crossed one hair's width. The cosmos extends for 100 yards in every direction. The crossing was not an arrival. It was the first step across a threshold so vast that the word threshold barely applies. It was the moment when the mission stopped being about what the probes could discover and started being about what they had become, objects falling outward through a space so enormous that the entire concept of destination becomes meaningless. As the power fades, as the instruments die, as the probes begin their millennia-long drift through the dark, the story shifts from scientific triumph to something no engineering team ever planned for and no mission document ever described. There is a room at the Jet Propulsion Laboratory in Pasadena, California, where a small team of engineers monitors two signals arriving from the outermost reaches of human experience. The room is not glamorous. It does not appear in recruitment brochures or feature in documentaries about the golden age of space exploration. It contains workstations, monitors, and the quiet hum of equipment performing calculations that have continued, with only minor interruptions, since the late 1970s. The signals these engineers track are extraordinarily faint. By the time they reach the Deep Space Network's 70-meter radio dishes, the largest steerable antennas on Earth, they carry less than 1/10 of a billionth of a trillionth of a watt of power. Extracting coherent data from this whisper requires some of the most sensitive receiving equipment ever constructed, combined with hours of signal integration to distinguish the spacecraft's voice from the natural radio hiss of the cosmos. This team, numbering fewer than a dozen full-time staff, supported by a modest budget that would not cover the catering costs of a major Hollywood production, is all that remains of the operational Voyager mission. Their job is to maintain communication with two spacecraft that are older than most of the people working on them, and they are engaged in a slow, methodical, carefully sequenced process of shutting things down. The power system that sustains both Voyager probes is a marvel of mid-20th century nuclear engineering. It is also dying. Each spacecraft carries 3 radioisotope thermoelectric generators, designated as RTGs, fueled by plutonium-238 in the form of pressed plutonium dioxide pellets. This isotope decays through alpha emission. Each atom of plutonium-238 spontaneously releases a helium nucleus, transforming into uranium-234 and releasing a small pulse of thermal energy in the process. Collectively, the trillions upon trillions of simultaneous decay events within each RTG produce a steady flow of heat, which thermoelectric couples, semiconductor junctions exploiting the Seebeck effect, convert into electrical current. The half-life of plutonium-238 is approximately 87.7 years. This means that roughly half of the original plutonium atoms have now decayed since the probes were fueled in the mid-1970s. But the power loss is not solely attributable to the diminishing plutonium inventory. The thermoelectric couples themselves degrade over time. Decades of exposure to radiation, thermal cycling, and the slow diffusion of materials across semiconductor junctions have reduced their conversion efficiency. The combined effect, less heat from declining plutonium, less efficient conversion of the heat that remains, produces a steady, irreversible decline in available electrical power. The rate is approximately 4 watts per year, and it has been constant, unyielding, and immune to any engineering intervention since the day of launch. The original 470 watts produced at launch was never a generous budget. For comparison, that figure is roughly what a single large household appliance consumes. The Voyager engineers had to run an entire interplanetary science laboratory, 11 instruments, heaters, computers, attitude control systems, radio transmitter, on less electricity than it takes to operate a typical home clothes dryer. Every watt was allocated with extreme care. Power margins were thin from the beginning. As of the mid-2020s, that output has fallen below 200 watts. This is not enough to operate all remaining systems simultaneously. It has not been enough for many years. The engineers have been managing the decline through a process that resembles triage on a sinking ship, deciding what to turn off, what to keep running, and what to sacrifice so that the most critical functions survive a little longer. The shutdown process began decades ago, so quietly that most of the public never noticed. The first major systems to go were the cameras. After Neptune, there was nothing left to photograph. The probes had passed the last planets, and the surrounding space offered no targets for visible light imaging at distances where exposure times would need to be impossibly long. The scan platform that aimed the cameras was powered down to conserve electricity for instruments that could still collect useful data about the magnetic, particle, and plasma environment of the outer heliosphere. The magnetometer, the cosmic ray subsystem, the plasma wave instrument, the low-energy charged particle detector. Since then, the shutdowns have continued in a careful sequence determined by scientific priority and power consumption. Heaters have been turned off one by one. Each heater protected a specific instrument or fuel line from the cold of deep space, where ambient temperatures hover just a few degrees above absolute zero. Turning off a heater saves a few watts of power but risks freezing the component it protected. Some instruments have continued operating at temperatures far below their design specifications, a testament to engineering margins built in nearly 5 decades ago. Others have not survived the cold. Each loss is permanent. There are no replacement parts. There is no repair mission. There is no second chance. The specific sequence of shutdowns tells a story of increasingly painful choices. The plasma science instrument on Voyager 1 failed in 1980, long before the heliopause crossing, which is why confirming that crossing required such indirect methods. The photopolarimeter on Voyager 2 failed during the Saturn encounter. The ultraviolet spectrometer heaters were turned off in the 2000s, allowing the instruments to cool to temperatures far below their design range. Remarkably, some continued to return usable data, even in this degraded state. a testament to engineering tolerances built in by designers who could not have anticipated this scenario. In 2020, the mission team turned off the heater for the cosmic ray subsystem on Voyager 2, dropping the instrument's operating temperature to -59 degrees Celsius, well below its tested survival limit of -45 degrees. The instrument continued working. No one could explain precisely why, except that the original manufacturer had built it with margins that exceeded the specification sheet. Each of these decisions extended the mission by months or years, but each one also narrowed the range of science the probes could perform. The triage is asymmetric and irreversible. Every instrument saved costs another instrument lost, and nothing that is turned off can ever be turned back on again. The decisions are made by the mission team on the ground, transmitted to the spacecraft via radio signal through the Deep Space Network, and executed by onboard computers running software that was originally coded in the 1970s, but has been updated and patched remotely over the decades. The commands travel at the speed of light, but require more than 22 hours to reach Voyager 1, and approximately 19 hours to reach Voyager 2. A simple command and confirmation cycle: send instruction, wait for execution, receive confirmation, takes nearly 2 full days for Voyager 1. Every interaction with the spacecraft unfolds in slow motion, across a communication lag so long that the engineers must plan each step with the care of chess players thinking several moves ahead. The computing infrastructure that supports this communication is itself a kind of time capsule. The onboard flight computers use an architecture and instruction set that predates the microprocessor revolution. The command computer and the attitude and articulation control subsystem each contain so little memory that a single low-resolution smartphone photograph would exceed their total capacity. The software is written in assembly language tailored to custom hardware that no manufacturer has produced in decades. On the ground, the situation is equally archaic by modern standards. The original mission control software was written in Fortran and has been maintained, patched, and adapted across multiple generations of computing hardware, from mainframes to mini-computers to modern workstations that emulate the behavior of machines long since scrapped. Engineers joining the Voyager team in recent decades have had to learn programming practices that were obsolete before they were born, studying documentation written by people who retired or died years ago. The institutional knowledge required to operate the mission exists in a chain of human memory and written records stretching back nearly 50 years, and that chain grows more fragile with every passing year. When the last engineer who understands the flight software retires, a layer of operational capability will vanish that no manual can fully replace. By 2025, Voyager 2 was operating with only a handful of active science instruments, and the engineering team had begun turning off heaters that protected the remaining ones. Voyager 1 retained slightly more power due to minor differences in its RTG manufacturing and thermal configuration, but the trajectory is identical for both, a slow, inevitable convergence towards zero usable power. NASA engineers estimate that by approximately 2030, both spacecraft will lack sufficient electrical output to operate any scientific instruments at all. The last sensor will fall silent. The last data point will be recorded. The final measurement of the interstellar magnetic field or cosmic ray flux will be transmitted to Earth and received by a dish antenna in the California desert or the plains of Spain or the Australian outback. And then, by approximately 2036, give or take a year or two depending on how aggressively the team continues to sacrifice heaters and non-essential systems, the probes will lack sufficient power to maintain their radio transmitters. The 23-watt signal that has connected these machines to Earth for nearly 6 decades will weaken below the threshold of detectability. The Deep Space Network's receivers will listen and hear nothing distinguishable from the background static of the universe. Mission controllers will attempt to send commands. There will be no acknowledgement. They will try again. Silence. At some point, and no one can say exactly when, because the transition will be gradual rather than instantaneous, someone will make the administrative decision to stop listening. When that moment arrives, it will not be dramatic. There will be no final burst of data, no farewell message composed by an onboard computer achieving unexpected sentience. No last photograph beamed home as a parting gift. The transmitter will simply grow too weak to produce a coherent signal above the noise floor. The spacecraft's radio voice, which has been growing fainter for decades, will drop below the limit of human detection and continue dropping. The probe will still be transmitting. The transmitter does not know it is no longer being heard, but the signal will be so feeble that no antenna on Earth or anywhere else could extract meaning from it. The whisper will become silence not because the speaker stopped talking, but because the listener can no longer hear. For the men and women who have spent years or decades maintaining this link, the approaching silence carries a weight that is difficult to articulate to anyone outside the mission. Suzanne Dodd, the current project manager, has described the work as a relationship, not a metaphor she uses lightly, but an honest characterization of what it means to communicate daily with an object that is slowly, irreversibly leaving. The engineers know every remaining subsystem by name, by behavior, by idiosyncrasy. They know which instruments run warmer than expected and which ones have surprised everyone by surviving conditions they were never rated for. They know the sound of the data when it arrives, not literally, but in the rhythms and patterns of telemetry that become familiar after years of monitoring. And they know, with the clarity that comes from staring at power curves and decay rates, exactly how the story ends. There is no rescue. There is no reprieve. The power will decline, the signal will fade, and the mission they have tended for years will slip beyond their reach. They are managing a farewell that has been unfolding in slow motion for decades, and they are doing so with a professionalism and steadiness that deserves more recognition than it typically receives. And then the longest phase of Voyager's journey will begin, because the loss of communication does not mean the probes stop moving. Nothing about the cessation of radio contact changes their velocity, their trajectory, or their physical existence. They carry no braking mechanism. No friction acts on them in the vacuum of interstellar space. No drag, no air resistance, no medium dense enough to slow them by any measurable amount over any human timescale. They will continue travelling at approximately 17 km per second for Voyager 1 and approximately 15.4 km per second for Voyager 2. Velocities that will remain essentially unchanged for millions of years. The only force acting on them will be the Sun's gravity, which at their current distance produces a deceleration so minuscule it is measured in millionths of a meter per second squared. Over the course of 1 million years, this gravitational braking will reduce Voyager 1's velocity by less than 1 km per second. The probes will slow down, but so imperceptibly that the change would be undetectable by any instrument aboard, even if the instruments were still functioning. For all practical purposes, the probes are coasting at constant speed through a medium that offers no resistance, on trajectories that are fixed by the laws of Newtonian mechanics and the initial velocity imparted by their launch vehicles and gravitational slingshots nearly half a century ago. This means that long after the mission ends, long after the last engineer retires or passes away, long after the Jet Propulsion Laboratory transforms into whatever institution succeeds it, long after the Deep Space Network antennas are decommissioned or repurposed, long after the administrative and political structures that funded the mission have dissolved into history, the probes will still be out there, still moving, still carrying their instruments, their golden records, their now inert plutonium, their etched plaques, their structural components, their wiring, their antenna dishes pointed back toward a planet that can no longer hear them. All of it drifting through interstellar space at speeds that outpace any vehicle ever built by human hands, but barely register against the scale of the distances involved. To understand how long this drifting phase lasts, and this is where the numbers begin to break human intuition, consider the distances that separate stars in our region of the Milky Way. The nearest known star system to the Sun is Alpha Centauri, at a distance of approximately 4.37 light-years. A light-year equals roughly 5.88 trillion miles. The gap between our Sun and its nearest stellar neighbour is therefore approximately 25.7 trillion miles. Voyager 1, travelling at roughly 38,000 miles per hour relative to the Sun, covers approximately 333 million miles per year. At that rate, crossing the distance to Alpha Centauri would require approximately 77,000 years. But Voyager 1 is not heading toward Alpha Centauri. Its trajectory carries it in the general direction of the constellation Ophiuchus, along a path determined by the geometry of its final planetary encounter at Saturn and the Sun's gravitational influence on its outbound course. In approximately 40,000 years, Voyager 1 will pass within roughly 1.6 light-years of a star called Gliese 445, a dim red dwarf currently located in the constellation Camelopardalis. That distance, 1.6 light-years, equals approximately 9.4 trillion miles. The probe will not enter that star's planetary system, if one exists. It will not be captured by its gravity. It will not orbit. It will pass through the distant outskirts of that star's gravitational neighbourhood and continue onward, unaltered, unaffected, unnoticed. Voyager 2 follows a different trajectory, heading generally in the direction of the constellation Sagittarius. In approximately 40,000 years, it will pass within roughly 1.7 light-years of the star Ross 248, another red dwarf, currently in the constellation Andromeda. The same conditions apply. No capture, no orbit, no meaningful interaction, just a geometric near-miss so distant that it would be invisible to any observer on either end. These timescales resist human comprehension, but they demand the effort. 40,000 years ago, anatomically modern humans were migrating across Ice Age Europe. The cave paintings at Lascaux would not be created for another 20,000 years. Agriculture did not exist. Writing did not exist. Cities, nations, religions, scientific disciplines, none of these had been conceived. The entirety of recorded human history, from the earliest Sumerian clay tablets to the device on which you may be reading these words, spans approximately 5,000 years. Voyager will drift for 8 times that duration before it even approaches the distant neighbourhood of another star, and it will not stop there. After those initial stellar near-passes, the probes will continue through the Milky Way galaxy on timescales that demand astronomical rather than historical language. Each probe will orbit the galactic centre, along with the Sun and every other nearby star, tracing a slow arc through the galaxy's disk at velocities determined by the combined gravitational influence of all the mass within their orbital radius. One complete orbit around the galactic centre takes approximately 225 million years, a period sometimes called a galactic year. The dinosaurs went extinct less than 1/3 of a galactic year ago. The Voyager probes, barring improbable collision with some interstellar object, will complete full galactic orbits. Multiple orbits. They will circle the Milky Way's centre while stars are born, burn through their hydrogen, and die, while nebulae collapse into new solar systems. While the galaxy itself continues its slow gravitational interaction with Andromeda, during all of this, the probes will be inert, the instruments will be dead, the cameras will be dark, the computers, even if structurally intact, will have no power to process a single bit of data. The transmitters will be silent. The golden records will be unplayable, not because they have degraded, but because no power exists aboard to spin them and no mechanism exists to broadcast their contents. The probes will be, in every functional and operational sense, debris. Sophisticated debris. Precisely engineered debris. Debris shaped by human knowledge, human ambition, and human hands. But debris nonetheless. The question of how long this debris will physically survive is one that engineers and physicists have examined with considerable care. In the interstellar medium, several degradation processes act on any solid object. Cosmic ray bombardment slowly damages crystalline structures and surface materials. Micrometeorite impacts, collisions with interstellar dust grains travelling at relative velocities of tens of kilometers per second, erode surfaces over geological timescales. The process is called sputtering, and it operates grain by grain, atom by atom, stripping material from exposed surfaces at rates that depend on the density of the local interstellar medium and the relative velocity of the dust. For an object the size and composition of a Voyager probe, these processes are extraordinarily slow. The interstellar medium in our galactic neighborhood is thin, roughly 1 atom per cubic centimeter in the denser regions, far less in others. Dust grains are sparse. Cosmic ray flux is constant, but the cumulative damage to macroscopic structures takes enormous spans of time to become significant. Engineers estimate that the Voyager spacecraft will remain physically recognizable, structurally intact, their major components identifiable, for hundreds of millions of years. The golden records, protected by their aluminum covers and shielded from the most intense radiation by the spacecraft's body, may survive even longer. Some analyses suggest the records could remain physically intact for over 1 billion years, though the fidelity of the encoded information would degrade long before the physical substrate failed. 1 billion years. The number demands contextualization. 1 billion years ago, the most complex life forms on Earth were single-celled organisms. Multicellular life had barely begun to experiment with its own possibilities. The entire Cambrian explosion, the rapid diversification of animal body plans that produced the ancestors of every complex creature alive today, was still 500 million years in the future. The Voyager probes will drift through interstellar space for a span of time that encompasses the entire evolutionary history of complex life on Earth, and potentially far beyond it. There is another dimension to this survival that compounds its strangeness. The probes cannot be retrieved. This is not a temporary limitation that future technology might overcome. It is a consequence of fundamental physics and practical reality so severe that the word impossible applies with unusual precision. Consider what retrieval would require. First, you would need to know exactly where the probe is. After loss of communication, the last known trajectory can be projected forward using orbital mechanics, but small uncertainties in velocity and position accumulate over time. After 1,000 years of unpowered flight, the positional uncertainty would be measured in millions of miles. After 10,000 years, the probe could be anywhere within an enormous volume of space. No beacon. No signal. No thermal signature. No electromagnetic emission of any kind. Finding a school bus-sized object in a search volume measured in cubic light-years is not merely difficult. It is, for any foreseeable technology, indistinguishable from impossible. Second, even if you could locate the probe, you would need to reach it. Voyager 1 is currently travelling at 17 kilometers per second away from the Sun. Matching that velocity, decelerating, rendezvousing, and returning would require a spacecraft with capabilities so far beyond current or projected technology that the scenario belongs to the realm of pure speculation rather than engineering planning. The energy requirements alone, accelerating a retrieval vehicle to interstellar velocities and then decelerating it, exceed anything achievable with chemical rockets, ion drives, or any propulsion system currently under serious development. The probes are gone. They have been gone since the moment of launch, in the sense that their trajectories were always one way, but the permanence of their departure only becomes fully apparent when the communication link dies. As long as the signal persists, however faint, however delayed, there is a thread connecting the probes to their creators. Data flows, commands are sent, engineers listen and respond. The probes remain, in some attenuated but real sense, part of human activity. When the signal stops, that thread snaps. The probes pass from the category of active mission into the category of object, a physical artifact drifting through the cosmos with no connection to the intelligence that created it. This transition, from mission to object, from participant to artifact, is what separates Voyager from every other human achievement in terms of temporal scale. Consider the most durable human constructions on Earth. The Great Pyramid of Giza has stood for approximately 4,500 years. It is impressive. It is monumental. It will eventually be eroded by wind, dissolved by acidic rain, crumbled by seismic activity, or subducted into the Earth's mantle by tectonic forces operating over millions of years. Even the most optimistic preservation estimates give it tens of thousands of years before significant degradation, perhaps 100,000 years before it becomes unrecognizable. The Voyager probes will remain structurally intact for a period roughly 10,000 times longer. The same comparison applies to every other human artifact. The Hoover Dam will last perhaps 10,000 years before geological forces reclaim it. The faces on Mount Rushmore will erode beyond recognition in approximately 500,000 years. The radioactive glass logs buried at nuclear waste repositories will remain hazardous for roughly 10,000 years before decaying to background levels. None of these timescales approach the projected physical survival time of the Voyager spacecraft. In the cold vacuum of interstellar space, protected from the weather, the water, the oxygen, the biological activity, and the tectonic forces that destroy every artifact on Earth's surface, the probes will endure on timescales that belong to geology and astronomy, rather than history. This durability has an emotional dimension that becomes more acute as you sit with it. Long after every building on Earth has crumbled, long after every digital archive has corrupted beyond recovery, long after every book has turned to dust and every language has been forgotten, the Voyager probes will still exist. They will carry forward into the deep future a physical record of human craftsmanship, the specific alloys, the particular wiring patterns, the precise mechanical tolerances achieved by technicians working in clean rooms in Pasadena in the mid-1970s. The probes will preserve the fingerprints, literally, in the oils left by human hands on interior surfaces of people who have been dead for centuries, then millennia, then epochs. They will carry these traces into a future that may not contain the species that left them. This is not speculation driven by pessimism about human survival. It is a straightforward consequence of the timescales involved. Whether humanity persists for another 1,000 years or 1,000,000 years, the Voyager probes will almost certainly outlast us. No mammalian species in the fossil record has persisted indefinitely. Even if humanity proves exceptionally durable, surviving for 10 million years, 100 million years, the probes will still be drifting, still intact, still carrying their cargo of sounds and images and engineered precision through a galaxy that has no knowledge of their origin. The probes will outlast their creators. They will outlast their creator's planet. In approximately 1 billion years, the sun's increasing luminosity will raise Earth's surface temperature to the point where the oceans evaporate and the atmosphere is stripped away. The planet that built the Voyager spacecraft will become uninhabitable. In approximately 5 billion years, the sun will die, swelling, shedding, and collapsing into a cooling remnant. The solar system as Voyager knew it, the Jupiter it photographed, the Saturn whose rings it mapped, the Neptune whose storms it measured, will be fundamentally transformed or destroyed. The probes will still be drifting. They will pass through regions of the galaxy that no human has ever named. They will traverse interstellar clouds of varying density. They will cross the paths of stars that have not yet ignited from collapsing gas clouds. They will drift through the expanding remnants of supernovae that have not yet exploded. They will be present for events of cosmic significance that no human consciousness will ever witness, and they will register none of it. No instrument will measure, no camera will record, no transmitter will report. The probes will be there, physically present in the universe, carrying the residue of human intention and human craftsmanship, and they will experience nothing, and no one will know where they are. The last trajectory data, archived on servers that will themselves degrade and fail within centuries, will grow increasingly imprecise as the millennia pass. The probes will become untraceable. Their positions will be unknown, not merely in the practical sense that no one is tracking them, but in the deeper sense that no calculation could determine their location with useful accuracy. They will become lost in the most absolute meaning of the word, objects whose existence is certain but whose location is unknowable. Here is the re-anchoring thought that belongs at the end of this phase of the story. The terrifying truth about Voyager is not how far it has travelled, though the distance is extraordinary. It is not the crossing of the heliopause, though that achievement was historic, the terrifying truth is the time. The span of Voyager's journey, measured from the moment of power failure to the eventual structural degradation of the spacecraft, exceeds every other human timescale by orders of magnitude. Every civilization that has ever risen and fallen on Earth could fit within the first fraction of a percent of the Voyager probe's projected survival time. Every language, every religion, every political system, every scientific paradigm that humanity has ever produced occupies a sliver of time so thin it would be invisible on any chart that included the full duration of Voyager's drift. The probes will keep going. They have no choice. They have no mechanism to stop, no destination to reach, no awareness that they are moving at all. They will simply persist, cold, silent, undetectable, carrying everything we gave them through a darkness that stretches beyond every human concept of endurance. And what they carry, the sounds, the music, the images, the greetings in 55 languages, transforms this story from engineering into something that touches the deepest questions humanity has ever asked about its own significance. Bolted to the side of each Voyager spacecraft, mounted on a bracket designed to survive the vibrations of launch and the thermal extremes of deep space, is a 12-inch gold-plated copper disc sealed inside an aluminum jacket. The jacket is electroplated with a thin layer of ultra-pure uranium-238, whose slow and predictable radioactive decay serves as a kind of cosmic clock. Any sufficiently knowledgeable finder, at any point in the future, could measure the ratio of remaining uranium to its decay products and calculate, with reasonable precision, how much time had elapsed since the record was assembled. Etched into the cover's surface are a series of diagrams, instructions for extracting and playing the disk, a pulsar map showing the position of the Sun relative to 14 rapidly rotating neutron stars whose unique rotational signatures serve as galactic landmarks, a schematic of the hydrogen atom in its two lowest energy states, providing a universal unit of measurement, and a diagram of the record's playback speed, reference to the fundamental transition time of the hydrogen atom. Inside the cover, the disk itself contains 115 images encoded as analog audio waveforms, photographs of Earth, of human beings, of animals, of architecture, of scientific diagrams, of mathematical concepts rendered visually. It contains spoken greetings in 55 languages, ranging from ancient Sumerian to modern Mandarin, each one a few seconds long, each one a human voice saying some variation of hello to an empty universe. It contains a 90-minute selection of music spanning cultures and centuries, Bach's Brandenburg Concerto No. 2, a Navajo night chant, a Peruvian wedding song, Chuck Berry's Johnny B. Good, Beethoven's Fifth Symphony, a raga performed by Surashri Kesabai Kirkar, and it contains a collection of sounds intended to represent the acoustic texture of life on Earth: wind, rain, thunder, surf, birdsong, the calls of humpback whales, footsteps, heartbeats, laughter, the first cries of a newborn child. This is the golden record. It is, by any measure, the most ambitious message ever composed, not because of its technical sophistication, which is modest by modern standards, but because of the silence into which it was launched and the time scale across which it must endure. The record was conceived and assembled in 1977 under the creative direction of Carl Sagan, who gathered a small committee of scientists, writers, artists, and musicians to decide what should represent all of human civilization on an object that might drift through interstellar space for hundreds of millions of years. They had approximately 6 weeks to make their selections, 6 weeks to distill the entire output of a species into a package that would fit on a 12-inch phonograph disc. The constraints were severe. The encoding method limited the number of images. The recording time limited the duration of music. The uncertainty about who, if anyone, might ever encounter the record meant that every choice had to balance cultural specificity against some imagined universal comprehensibility. The selections were necessarily arbitrary. Which music? Whose voices? Which images? Every inclusion reflected the preferences and blind spots of a particular group of people working under extreme time pressure in a particular cultural moment in a particular country. They included Western classical music, but relatively little popular music. They included greetings in dozens of languages, but could not include every language spoken on Earth. They chose the sound of a kiss and the brain waves of a young woman, Anne Druyan, who would later become Sagan's wife, recorded as she thought about the history of Earth and what it meant to fall in love. They selected a photograph of a woman nursing an infant, then reportedly removed it under pressure from NASA administrators who worried about the appearance of nudity on a taxpayer-funded spacecraft. They included mathematical notation but no religious texts. They included a photograph of a supermarket but not a photograph of war. Every decision was a compromise. Every inclusion implied an exclusion. The record is not a complete portrait of humanity. It is a curated selection, a mixtape assembled by a small group of well-intentioned people who understood that completeness was impossible and settled instead for sincerity. One selection on the record stands apart from all others in its intimacy. On June 3rd, 1977, Anne Druyan, a member of the creative team and a woman who had, 2 days earlier, fallen in love with Carl Sagan during a late-night phone call, sat in a laboratory at New York University while an EEG machine recorded the electrical activity of her brain for 1 hour. She had been asked to meditate on a series of prepared topics: the history of Earth, the emergence of life, the development of human civilization. But she later described how her thoughts kept returning to the private upheaval of those few days, the astonishment of new love, the vertigo of realizing that her life had just changed irreversibly. The resulting recording, a compressed analog representation of 1 hour of human neural activity, was included on the Golden Record alongside Bach and Beethoven. Druyan has said that she hoped, perhaps irrationally, that some future intelligence might be able to decode the EEG and recover something of what she was feeling. The probability of this is, by any scientific measure, 0. Brainwave patterns are not a language. They do not encode specific thoughts in a form that could be reconstructed by an outside observer, human or otherwise. But the recording persists on both golden records, 1 hour of a woman falling in love, rendered as electrical noise, drifting through interstellar space aboard 2 machines that will outlast every human relationship by millions of years. It may be the most private artifact ever made public, and the most temporary emotion ever committed to a permanent medium. The Golden Record is overwhelmingly discussed in the context of extraterrestrial contact. Popular accounts frame it as a message in a bottle, cast into the cosmic ocean, waiting to be discovered by some alien intelligence that will decode the instructions, build a playback device, listen to Chuck Berry, and understand something fundamental about who we were. This narrative is romantic and compelling. It gives the record a sense of purpose, even destiny. Somewhere, someday, someone will find it. Someone will hear Beethoven performed by human hands for the first time. Someone will see the photograph of a sunset over the Pacific and feel whatever an alien mind feels when confronted with alien beauty. But this framing, however emotionally satisfying, obscures a reality so stark that it fundamentally changes the meaning of the record. The probability that any intelligence will ever encounter either Voyager probe is, by any honest assessment, indistinguishable from 0. This is not pessimism. It is geometry. Interstellar space is not a corridor. It is not a shipping lane. It is not a region through which objects pass with any frequency that would make random encounters plausible. It is a volume so vast and so empty that the word empty fails to capture its true character. The average distance between stars in our region of the Milky Way is 4 to 5 light years, roughly 25 to 30 trillion miles. The Voyager probes are each smaller than a school bus. After their power systems die, they will emit no radiation. They will produce no light. They will generate no heat above the ambient temperature of the surrounding medium, which hovers a few degrees above absolute 0. They will reflect no starlight in any detectable quantity. They will be, electromagnetically speaking, invisible, dark objects drifting through a dark medium across distances that make the word needle in a haystack seem laughably inadequate. The projected near passes of other stars compound rather than relieve this isolation. The closest Voyager 1 will come to another star in the next 40,000 years is roughly 9.4 trillion miles, a distance that sounds like proximity only in the language of interstellar astronomy. At human scales, it is an absurdity. The odds that any hypothetical civilization in that star's vicinity would detect a cold, silent object no larger than a delivery truck passing at that range are not merely low. They are effectively non-existent. The object produces no signal, it carries no beacon, it emits nothing. It is a dark speck drifting through a dark void at a distance so great that the finest telescopes humanity has ever built could not detect it from that range. Voyager 2's trajectory offers similarly negligible prospects for encounter. And after these initial stellar passages, if passage is even the right word for events separated by trillions of miles, the probes will continue through the galaxy for millions and billions of years, each one tracing a slow orbit around the galactic center, drifting through interarm voids and spiral density waves, passing through regions of higher and lower stellar density without ever coming close enough to any star for detection to be remotely plausible. The mathematics of random encounter in three-dimensional space work decisively against contact. Even if the galaxy contained billions of spacefaring civilizations actively searching for interstellar artifacts, a scenario that vastly exceeds any reasonable estimate, the volume of space is so enormous, and the probes are so small and so silent that the expected time until detection would exceed the current age of the universe by many orders of magnitude. The golden record will almost certainly never be played by anyone other than the humans who recorded it. This realization does not diminish the record, it transforms it. If the golden record is not realistically a message to extraterrestrial intelligence, then what is it? The answer, once you sit with the question long enough, is both simpler and more profound than the alien contact narrative suggests. The golden record is a message from humanity to itself. It is a statement of identity composed at a moment when a species first achieved the technological capability to send an object beyond the reach of its own star. It is a self-portrait painted not for an audience but for the act of painting, a declaration that we existed, that we made music, that we loved, that we wondered about the cosmos, and that we chose to say so even though no one was likely to hear. The committee that assembled the record understood this, at least intuitively. Sagan wrote that the launching of the golden record was a hopeful rather than a practical act. The selections were not optimized for alien comprehension. They were optimized for human meaning. The music was chosen because it moved people, not because it would be decodable by a non-human intelligence. The sounds of earth, rain, wind, frogs, crickets were included because they represented the acoustic environment of the only world humans had ever known, not because they carried information that an alien civilization would find useful. The greetings in 55 languages were expressions of human diversity and goodwill, not data packets designed for maximum interstellar bandwidth efficiency. Certain selections reveal the committee's instincts with particular clarity. They chose Dark Was the Night, Cold Was the Ground by Blind Willie Johnson, a 1927 recording of a slide guitar piece with wordless vocal humming that Sagan's committee felt captured something universally recognizable about loneliness and yearning. Johnson was a street musician who died of poverty and exposure after being denied hospital admission, reportedly because of his race. His music, rejected by the institutions of his own time, now travels farther from Earth than any human creation in history. They chose an Azerbaijani bagpipe performance, a piece of Chinese Shin music dating to approximately the 5th century BCE, and a pygmy girl's initiation song recorded in the forests of Central Africa. They chose a photograph of a woman in a supermarket, a page from Isaac Newton's treatise on mechanics, an image of the planet Earth from space, and a photograph of a man from Guatemala. Each selection was an act of assertion, a claim that this sound, this image, this fragment of human experience deserved to represent the species. The committee could not have agreed on which selections were most important. They did not need to. The power of the record lies not in any individual track, but in the totality, the accumulated evidence that a species existed which made music, grew food, studied physics, and tried to say hello. The record, in its deepest sense, is an act of witness. It says, this is what it sounded like to be alive on Earth. This is what our music sounded like. This is what our world looked like. This is what our voices sounded like saying hello. And it says these things knowing, or at least suspecting, that the audience is the silence itself. This interpretation transforms the golden record from a hopeful outreach into something far more emotionally complex. Attached to a machine that will drift in silence for millions of years, the record becomes a monument to the distance between intention and outcome, between what we hoped and what is likely. The committee imagined contact. The physics guarantees solitude. The record will survive, physically intact, its grooves still carrying the encoded waveforms of Bach and Beethoven and Berry, for longer than the civilizations that produced every piece of music it contains. The Brandenburg Concerto will outlast the nation of Germany. The Navajo night chant will persist after every Navajo speaker is gone. The whale songs will endure long after the species that sang them has been silenced by extinction or evolution. The record will carry these sounds through a cosmos that cannot hear them, on a journey that has no audience, aboard a vessel that has no crew. And the poignancy of this, the almost unbearable tenderness of sending music into a void that will never appreciate it, is precisely what makes the golden record one of the most emotionally significant objects ever created. It is not a message, it is a love letter written in the full knowledge that it will never be read. But the golden record is only one element of the broader existential weight that Voyager carries forward into the interstellar dark. The deeper question is not what the probes carry, but what their continued existence means, and specifically, what it means that a human story is now unfolding without humans in it. Consider what has happened. A species evolved on a small rocky planet over the course of several 100,000 years. It developed language, tools, agriculture, mathematics, science, engineering. It built machines capable of leaving its planet's gravitational field. It aimed two of those machines outward, toward the boundary of its star's influence, and gave them enough velocity to escape. Those machines crossed the boundary. They entered the space between stars. They will continue traveling through that space for a duration that exceeds the entire evolutionary history of the species that built them. At some point during this journey, perhaps within a few centuries, perhaps within a few millennia, perhaps within a few million years, the species that built the probes will cease to exist. Not necessarily through catastrophe. Species end. They evolve into successor species, or they go extinct, or they transform themselves through technology into something unrecognizable. The average persistence time for a mammalian species is 1 to 2 million years. Homo sapiens has existed for roughly 300,000. Even extraordinary longevity, tens of millions of years, would represent a fraction of the time the probes will drift. This means that the Voyager probes will, with near certainty, outlast their creators. They will carry the golden record, the etched plaques, the structural evidence of human engineering, and the literal fingerprints of their assemblers through a future that does not contain the species that left those marks. The probes will become orphaned artifacts, objects whose creators are gone, whose purpose is extinct, whose meaning has no one left to interpret it. This is not a failure of the mission. It is the mission's most profound consequence. Voyager was designed to explore the outer planets and study the boundary of the heliosphere. It succeeded at both objectives beyond anyone's expectations. But in succeeding, it created something no one planned for, a human presence in the universe that persists independently of human existence. The probes are the first human objects to achieve a kind of autonomy from the species that made them, not through artificial intelligence or self-replication, but simply through the physics of motion in a vacuum. They do not need us to continue. They do not need anyone to continue. They will continue because nothing can stop them. There is a concept in philosophy called the ship of Theseus, a thought experiment about whether an object that has had all its components replaced is still the same object. Voyager presents a different and perhaps more disturbing version of this puzzle. The probes have not been modified. They remain physically the same machines that left Earth in 1977, minus the plutonium atoms that have decayed and the surface molecules that have been sputtered away by cosmic ray impacts. They are, in material terms, the same objects, but their context has changed utterly. The civilization that built them may be gone. The star they launched from may have changed. The planet where they were assembled may be uninhabitable. Everything that gave the probes meaning, the scientists who designed the instruments, the engineers who built the structure, the committee that chose the music, the taxpayers who funded the mission, the species that conceived the entire enterprise, may have vanished. What remains is an object, a cold, silent, perfectly preserved object, drifting through interstellar space, carrying a record that no one will play, a plaque that no one will read, a message that no one will receive. It is a monument without visitors, a time capsule without a future audience, a memorial to a species that may have no one left to mourn it. The Golden Record was not humanity's first attempt at interstellar communication. 5 years earlier, the Pioneer 10 and Pioneer 11 spacecraft, launched in 1972 and 1973 respectively, each carried a small gold anodized aluminum plaque designed by Carl Sagan and Frank Drake and illustrated by Linda Salzman Sagan. The plaques bore engraved images of a nude man and woman, a schematic of the solar system showing the spacecraft's origin, a diagram of the hydrogen atom's hyperfine transition, and a pulsar map similar to the one later used on the Voyager record cover. The plaques drew public controversy at the time. Some critics objected to the depiction of human nudity, while others questioned the assumption that line drawings would be comprehensible to a non-human intelligence. But the plaques represented a first draft of an idea that the Golden Record would expand enormously, the notion that a departing spacecraft should carry some deliberate representation of its makers. Where the Pioneer plaques were spare and diagrammatic, a schematic greeting, a cosmic calling card, the Golden Record was expansive and emotional, saturated with music and sound and image and voice. The evolution from plaque to record mirrors a shift in ambition, from merely identifying ourselves to attempting to convey what it felt like to be us. Both artifacts now travel through interstellar space on diverging trajectories, 4 silent messengers carrying 2 different versions of the same impossible hope. And yet, and this is the turn that prevents the story from collapsing into pure despair, there is something in the existence of the probes that resists nihilism. The Voyager spacecraft are the farthest, longest-lasting evidence that a particular arrangement of matter on a particular planet achieved something extraordinary. It became aware of the cosmos. It understood enough physics to leave its own star system, and it chose to send a record of its existence into the dark. The probes do not need an audience to validate this achievement. The act itself, the reaching, the launching, the recording, the choosing, carries its own significance regardless of whether anyone ever finds the result. The Golden Record contains a message from then-President Jimmy Carter that reads, in part, "This is a present from a small, distant world, a token of our sounds, our science, our images, our music, our thoughts, and our feelings. We are attempting to survive our time so we may live into yours." The language assumes a recipient. It imagines a future audience capable of understanding the message and appreciating its origins. But strip away that assumption, and the statement still resonates. We are attempting to survive our time. That impulse, the desire to persist, to leave a mark, to say we were here, is as fundamental to human nature as language or tool use. The Voyager probes are the purest physical expression of that impulse ever created. They will persist longer than any other human artifact. They will travel farther than any other human creation, and they will do so carrying not weapons, not territorial claims, not advertisements, but music. Greetings, the sound of rain. There is a famous photograph in the Voyager archive that has become one of the most widely reproduced images in the history of science. On February 14th, 1990, at a distance of approximately 3.7 billion miles from Earth, Voyager 1 turned its camera back toward the inner solar system. The image it captured shows Earth as a tiny speck, less than a single pixel in extent, suspended in a scattered beam of sunlight reflected within the camera's optics. Carl Sagan, who had campaigned for the photograph to be taken, called it the pale blue dot. He wrote about it with a clarity and emotional precision that has rarely been matched in scientific writing. That dot, he said, is here. That is home. That is us. Everyone you love, everyone you know, everyone you have ever heard of, every human being who ever was, lived out their lives on that mote of dust suspended in a sunbeam. What Sagan articulated, and what the photograph itself embodies, is the relationship between scale and meaning that defines the Voyager story. The dot is tiny. It is almost invisible. It is lost against the vastness of even the inner solar system, let alone the interstellar distances the probe has since traversed. And yet everything that has ever mattered to any human being occurred on that dot. Every war, every love affair, every symphony, every prayer, every scientific discovery, every act of cruelty, and every act of kindness, all of it took place on a world so small that from a distance of 4 billion miles it nearly disappears. The photograph was taken during the act of departure. Voyager looked back once, briefly, at the world that had built it. Then the camera was powered down permanently. There was nothing left to photograph, and the power was needed elsewhere. The probe turned away from Earth and continued outward. It has not looked back since. It cannot look back. The camera is dead, the power is failing, and the distance now separating the probe from its home world has grown from 4 billion miles to more than 15 billion. The pale blue dot, already nearly invisible at the time of the photograph, has long since disappeared entirely, too far away, too faint, too small to register on any instrument the probe carries. This is the image that should accompany every thought about Voyager's future. A machine built on that dot, carrying the sounds of that dot, launched by the inhabitants of that dot, now drifting through a darkness so vast that the dot itself has vanished from view. The connection is severed, not by choice but by distance, by time, by the fundamental geometry of a universe that permits departure but not return. Right now, at this moment, Voyager 1 is approximately 165 astronomical units from the Sun, roughly 15.4 billion miles. It is moving away at approximately 17 kilometers per second. It still receives occasional commands from a team of engineers who have spent their careers maintaining a link to a machine older than most of them. The remaining instruments, a magnetometer, a cosmic ray detector, a plasma wave sensor, still return data about the interstellar medium. The power is fading, the budget is shrinking, the team is aging. Within approximately 10 years, the last instrument will be switched off or will fail as its heater is sacrificed to keep the transmitter alive a little longer. Within approximately 15 years, the transmitter itself will fall below the detection threshold of every antenna on Earth. The Deep Space Network will listen one final time and hear nothing. A report will be filed. A press release will be issued. The mission will be declared complete, and then Voyager will drift. It will drift past molecular clouds where new stars are slowly condensing from hydrogen and dust. It will drift through regions of the galaxy where no star has shone for millions of years. It will drift while ice ages come and go on Earth, while continents rearrange themselves, while species evolve and go extinct in patterns no one can predict. It will drift while human civilization transforms or collapses, or ascends into forms we cannot imagine. It will drift while the sun slowly brightens, while Earth's oceans boil away, while the inner solar system is consumed by the red giant, our star will eventually become. It will drift after all of that, after the sun has died, after the solar system has dispersed, after the Milky Way has merged with Andromeda and the combined galaxy has settled into a new configuration. The probe will still be there, cold, dark, intact, carrying its golden record through a universe that has forgotten what music is. This is humanity's longest journey, not because of the distance, though the distance is extraordinary, not because of the speed, though the speed is remarkable, not because of the science, though the science was transformative. It is humanity's longest journey because it is essentially irreversible, a human story that continues without humans on a timescale that makes every lifetime feel microscopic. A small machine, carrying the sound of rain and the music of bark and the heartbeat of a species that once looked up at the stars and wondered if anyone was listening, falling endlessly through interstellar space toward no destination, witnessed by no one, answering a question that no one asked with a reply that no one will hear. The probes are still out there tonight, still moving, still carrying everything we gave them, and the universe stretches ahead of them, silent, patient, and immense, with no ending, no audience, and no return.